Okay, so actually I joined Penn State 2 years ago. Time flies. Welcome, I'm Hong Hu from Penn State, and today I'm going to share the work automatically diagnosing use of the free box via reference miscounting detection on binaries. So these days we have seen so many use of the free box. They're so popular. Actually, from this report of Microsoft, we can see they are always popular in the last decades. And even worse, these bugs are highly exploitable, which means attackers may use this bug to hack our system, no matter using Mac, Windows, or Linux. And from the same report, you can say use of free bugs is the most likely exploited after the release of a patch. So because of this problem, you may wonder why we have use of free bugs. What's the root cause? So based on the informal definition, use of free means use a dangling pointer after the referred object has been freed. So intuitively, you believe the problem is the free, right? The object is being freed, but still use it. How dare you? So the dangling use has been widely adopted to detect use of free bugs in a lot of previous work. But actually, we wonder, is that possible the free is wrong? Which means maybe the object is freed too early. That's why all the use after that is illegal. So we call this a prematurely free, and we realize there's no previous work trying to understand the root cause this way. So we propose a tool called FreeWill that trying to diagnose the prematurely free caused use of free bugs. So we realize the reference miscounting could be the common reason leading to prematurely free. And we design a tool to detect the reference miscounting, and we can suggest the possible patches. We applied our tool on a large number of bugs from browsers, operating systems, and language interpreters, and we can finish analysis within reasonable time and provide useful diagnoses and patches. So let's start with some background of reference miscounting. So this is a mechanism actually designed to help programmers to manage memory. So the idea is to associate a counter with each heap object. When programmers create a new reference of the object, they should increase the counter. And when they destroy a reference, it should decrease the counter. And when the counter is reduced to 0, it should free the memory, which means the program is not using this object anymore. So this method is widely used in many complicated systems, for example, Linux. Here is the Linux structures, and this is a common structure used in Linux that have the member called keyref, used for reference counting. And they have this keyref get to increase the counter, and they have the keyref put to decrease the counter. And if the counter is 0, they're going to free the memory. So you can see these mechanisms require the programmers to decrease the counter or increase the counter manually. And you can imagine programmers, they may make mistakes and lead to bugs. So we call this problem the reference miscounting. There are two types of miscounting. The first case, programmers may forget to decrease the counter when they destroy a reference. So in this case, the memory can never be released. This is going to have the memory leak issue. On the other side, programmers may forget to increase the counter when they create a new reference. And in this case, the value of the counter cannot reflect the real number of uses in memory of this object. And this will lead to prematurely free and finally use of free bugs. So here's an example. This is a real use of free bug in Linux last year. And the problem is programmers forget to increase the counter when they create a new reference. And the solution on the right side is just to simply increase the counter and the bug is gone. So you may think this is quite straightforward. Just need to scan the execution and find any missed reference counting. Then you find the root cause. Unfortunately, it's not that easy because not all missed reference counting are bad. The problem is reference counting is good for programmers, but it's not free. It can lead to performance overhead, which could be 30% slowdown of the execution. So programmers that are eager to skip or omit some unnecessary reference counting, you can find online the complicated guidelines to tell programmers, hey, you can avoid the reference counting this way. But unfortunately, this will lead to problems and mistakes. So our question is how to identify which missed reference counting is the buggy one, is the one leading to prematurely free. So our solution to this challenge is to propose a model to describe what is the legal omission of reference counting. And we list them here. The first one is the overlapping rule. For them here, we have two references, R1 and R2. So ideally, we should have the reference counting for both R1 and R2's creation and destruction. But in fact, if we know they are overlapping, we can skip some references. For example, the decrease for R1 destruction or the increase of R2's creation. So in this case, the counter is still balanced. There's no risk because you know they're always overlapped. This is one rule. And similarly, it could be have multiple references overlapped this way. And actually, you can skip all the reference counting in the middle and only keep the ones on both sides. Another rule is a contingent rule, where this one reference, like R2 here, is contained in the lifetime of another reference. So in this case, you can completely skip the reference counting for R2. You are still safe. And there could be more complicated cases, but we can still clearly define what is possible, what is not allowed. So based on these rules, we propose an algorithm to scan the execution trace of the program and trying to explain why some reference counting is skipped. If we cannot explain, we believe this could be the root cause of premature free. So the detail of this algorithm is in the paper. You are encouraged to check the details if you're interested. So here is an example. This is just the lifetime of one user-free object, and there are 5 references from R0 to R4. And for R0 and R1, we can use the overlapping rule to explain why some reference counting behavior is skipped. It's okay because it follows our rules. And for R2, it is contained in the lifetime of R1 and R0, so it's okay to skip the reference counting behaviors. But for R3 and R4, we cannot find any rules to explain why programmers skip the reference counting, so this could be the root cause of premature free or use-of-free bugs. So this is our algorithm to detect the root cause that lead to premature free. And we plan to apply this rule to program binaries. As you can imagine, it's not that easy. There are some challenges for them. How do you find the reference counters? How do you find the reference counting behaviors? And how do you correlate this reference counting to reference creation and destruction? So if you have source code, it's relatively easy. You can use the annotation or debug information to help. But with the binary, we have to rely on the heuristics. So the first heuristic we use is to analyze the data flow of the program execution. And for example, here we have all the values of structure members. And if we can see some pattern like this, the value is changed in a fixed step like this, 0 to 1 to 2 to 1 to 2 to 1 to 0. They're always being increased or decreased by 1. We suspect this could be a reference counter. Of course, this is not enough. For example, here in the IE browser, we find this counter implemented this way, that the last 3 bits is for flags. It's not for counters. So most of the time, you see the value is changed by 8, but sometimes it could be changed by 2 due to flag operation. So to solve this problem, we propose a second heuristic called the control-dependent free, which means that we're going to check whether the program are going to compare the value with some other constant, and if they match, they're going to free the memory. If they match both heuristic, we believe this could be a reference counter. And next, we want to correlate the reference counting behavior to the reference creation and destruction. Then we can analyze them using our algorithm. So the basic idea is to use the distance. We want to find the closest reference counting and the reference creation and destruction and trying to connect them. And sometimes the reference counting could be done inside a wrapper function. So in this case, we are going to calculate the distance between functions instead of instructions. So this is the basic idea. More details you can find in our paper. So based on our algorithm, we design this tool FreeWill. We are going to run the program with the POC and get the execution trace. Then we're trying to identify the use of the free object. We're trying to identify the reference, and we want to correlate the reference with the reference counting behaviors, and finally, use our algorithm to detect any miscounting behavior that lead to premature free, and finally, use of free bugs. And we do evaluation to understand how good is our tool regarding 3 questions: how accurate is our root cause analysis, and how effective is our patch suggestion, and finally, how accurate is our reference recovery and the reference counting correlation. We applied our tool to 76 bugs from the browsers, operating systems, and language interpreters, and here's the result. So among 76 bugs, we have 48 bugs caused by reference miscounting, and this table shows more details. But overall, there are 36 bugs that is due to the programmers forget to increase the counter and forget to decrease the counter, which means there's no ref counting at all for this new reference. And for another 12 bugs, programmers do not increase the counter, but they decrease the counter for destruction. That introduces the imbalance. And for another 18 bugs, they do not use ref counting, so just a normal managed by the programs themselves, and there's no reference counting issue at all. And also we're trying to understand the accuracy of a bug patch suggestion. So we check auto-generate 71 patches, and we manually check them and compare with the official patch. It turns out 56 of them is actually matched with the official patches released by the vendor. And here's one example. So here, this push instruction actually puts a pointer on the stack, which effectively creates a new copy of the reference. However, there's no reference counting, no increasement or decreasement. So we suggest that we should add the increasement and decreasement to this argument to avoid bugs. And actually, we checked the patches from Microsoft. They indeed also use the same method to fix this bug. And the last is just some statistics of our detection. So basically, on average, for each user-free object, we see there are about 2,000 references created and destroyed along the execution. And in one execution trace, we find 543 objects, and only 65 of them are ref-counted. Others are not ref-counted. And also measure the accuracy of the content detection. It turns out the control-dependent free is more accurate than the fixed step changing to identify counters. So in summary, in this work, we propose a tool, FreeWill, that can diagnose user-free bugs due to premature free. And we identify the reference miscounting is a common reason leading to this problem. And we design a tool to automatically detect reference miscounting, and we can suggest the possible patches. And we apply the tool on large programs and bugs, and we can finish this in reasonable time and with good patch suggestions. That's all I want to say, and thank you for your attention. I'm ready for questions.